And thanks a lot to the organizers for this great edition of quantum error correction. I also want to congratulate the organizers for the ordering of the talks this morning, because this talk is going to follow very much the one of Fernando previously, in the sense that it's not going to be so much focused on actually using codes for quantum computation, but really understanding physics through the spectacles of error correcting. Most of you should be thinking, when they see the title local approximate error correcting code, and especially with approximate, that it's mostly going to be about epsilons and deltas. And you'd be absolutely right in thinking this, because it really is just about epsilons and deltas. But as the theory advances, and as we'd like to establish tighter and tighter correspondences or insights between physics and error correction, I think we need to take these epsilons and deltas seriously. But since it is a pretty technical subject, the way I'm going to introduce it is sort of chronologically how me and my collaborators, I forgot to mention, collaborators are Steve Flamia, Jungwon Ha, and Isaac Kim, went about this. And the way we got onto this topic is we noticed that the definitions of local topological quantum order and error correction are identical in the exact case, but they seem to be slightly different in the approximate case. And we were wondering, well, is this something which is really worth looking into, or is it just sort of a curiosity of the definitions? So I looked a bit into the literature, and we found this wonderful example that's, what is it now, over 10 years old, by Crépeau-Gottesman, that makes the following observation. An exact error correcting code cannot correct more than n over 4 arbitrary errors in the quantum setting. And this is largely due to the no cloning theorem. However, a classical error correcting code can correct up to n over 2 errors. And what Crépeau and al. Did is they constructed an approximate quantum error correcting code that can correct up to n over 2 arbitrary quantum errors. So it really showed that there might be a separation between the approximate setting and the exact setting. Now, this result can be understood as a trade-off bound. And what we set out to understand is, can there also be a fundamental difference between the trade-off bounds we know for topological quantum codes and some possible trade-offs for approximate local codes? Now, I'm not going to be very specific in what I mean by a topological code, except that it's defined on a lattice by local operators. Now, what is known in the exact case is that for commuting projector codes, these include the toric code and Levin-Wen models, among others. I wrote it in 2 dimensions. There are also higher dimensional analogs. The length of the code, the distance of the code, and the number of encoded qubits have to satisfy this relation. So the number of qubits times the distance squared has to be smaller than some constant times n as the system scales. And the toric code saturates this bound. For subsystem codes, Sergei constructed an example where this weaker bound is saturated. And for classical codes, an even weaker bound is saturated, and that is essentially the classical analog of the qubit code, of the Ha code. The question is, where do approximate codes sit? And we were sort of hoping that they would sit somewhere between these commuting projector codes and classical codes or subsystem codes, just based on the insight by Crépeau and Gottesman. But you'll see that, in fact, they don't. They really behave very much like exact codes with a bunch of epsilons and deltas. So before actually getting to the definition of approximate local error correcting codes, I just want to review what we know about the definitions of error correction for local commuting projector codes. So local commuting projector code is defined by operators that commute, and the code space is defined by the eigenvalue 1 code space of all these operators. And I'm only going to focus on erasure errors. And so what we've discovered over the years is that there are a number of equivalent definitions. There's a bit of a wall of text, so I'll walk you through it. The first definition is topological quantum order. And what topological quantum order tells you is that if you have two code states, they cannot be distinguished by a local observable. And here I consider the local observable on A on the lattice ABC. Second equivalent definition is decoupling, and it says that for any code state, it can also be mixed, the mutual information between A and C, and this R is a purification of your code state. Of course, in the case of pure states, it's going to be trivial, but in the case of mixed states, you're going to need a purification, is equal to 0 for a critical finite distance, well, beyond the critical finite distance, which is just given by the support of the commuting projectors. Third equivalent definition is what I'll just call error correction. It's sort of the most intuitive definition, is that if you erase a local region, then you can recover that information just by accessing region A and B. This is related to what Fernando was talking about, local correction. Fourth equivalent definition is that there exists a unitary acting only on B, which completely disentangles A and C. And then fifth equivalent definition is the so-called cleaning lemma, and it says that for any logical unitary U that acts on the whole system, you can define a logical unitary V, which only acts on BC, but acts identically on the code subspace. And in the case of the toric code, it's very intuitive. If you have a logical operation which touches a correctable patch, you can always move it around the patch. And on the code subspace, it's going to act in exactly the same way. And so our basic question is, how many of these properties can we actually extend to the approximate setting? For anyone who's looked a bit in the approximate quantum error correction literature, they'll realize that there are many definitions, and every definition is sort of fine-tuned to the application you want. So the fine-tuned application we want is to focus on these trade-off bounds. So in order to define the necessary properties we need, I want to go over this trade-off bound. It's also one of the most beautiful proofs in this field, I find. And it basically relies on three properties. So I'll present a proof which is slightly different from the original one, but in essence it's the same. And it's properties of exact codes, which are the expansion bound, the union bound, and some clever counting of degrees of freedom. So what does the expansion lemma tell you? It says that if you consider a lattice system consisting of concentric regions A, B, C, and D, where there's actually a separation between A, B, C, and D, if you know that A is correctable, and B is correctable, and B surrounds A or shields A from C, then A and B will also be correctable. And the easiest way to prove this is to note the first definition of the correctability of A, the fourth definition of correctability for A, which says that you can disentangle A and CD with a unitary on B, then you trace out B and you get this relation for some state omega only acting on A. And the second definition is that there exists a completely positive trace-preserving map acting only on ABC, which recovers the erasure of the B region. And then what we want to show is that there exists a completely positive trace-preserving map only acting on regions A, B, and C that correct for the erasure of AB. And we can just simply define this map to be this, and a little bit of algebra convinces you that this is true. So here we use definitions 4 and 3 from above. The union lemma tells you that if a region A is correctable, having only access to A in a region around A, and a region B is correctable, and that these two regions do not overlap on the lattice, then they're jointly correctable. And then the rest of the proof is a very clever trick of counting degrees of freedom. So to say that a code has distance D tells you that you can erase any D sites and still recover the information. But it doesn't tell you that there aren't some configurations where you can erase many more than D sites and still recover the information. And in particular, here we want to consider the largest square regions that you can still correct. And in order to create these largest square regions, we start with a first square with D qubits in it. And we sort of grow it and grow it and grow it as much as we can. And you can easily convince yourself that the largest you can grow it is when the boundary around these squares is the size of the distance. So it tells you that the largest squares you can build have side length proportional to the distance. And from the union lemma, we take the largest squares that are correctable, and since they're not overlapping in this configuration of x, y, and z, these different squares are going to be jointly correctable, and the same is going to be true for y. And then from some clever manipulation of mutual information, you get that the number of qubits that you can that can be in the code space is bounded by the size of z. And then you just count the smallest, you sort of want to maximize the size of x and y to get these z regions as small as possible, and you end up with the standard bound. Okay. Let's try to move on to approximate error correction. So we're going to take as our basic definition the existence of a recovery map. And we're going to define it as follows. I'll just postulate. So we need to consider the distance between the state where we erased region A, and then we tried to recover it with a CPT map, and see how far it is away from the original state. And now the distance measure we're going to use to compare two states is the Beer's distance. And right now, I'm just saying that this is the one we're going to use. It should be a bit strange to people in the audience because we're so used to using trace norms or diamond norms for channels, but this is going to be the relevant one. And here we always consider a purification system R. So this is a stabilized distance like the diamond norm. But you might guess that we need something just a bit stronger. So in the previous definition, there's no notion of locality. You're saying, can you correct for region A by having access to the information in the entire system? And in this next definition, which is local approximate correctability, it's essentially the same thing, but we only allow the recovery map to act on A and B. And okay, it's not obvious yet, but somehow the error in the correction you'd like to scale with some property of the system. You'd like it to scale with the size of the system, or in particular here, what we'd like it to scale with is how large B has to be. So this intermediate region between A and C, we allow the local recovery map to act on. Okay. The reason why we choose the Beer's distance is because it's the only distance measure which gives us an exact equality in this information disturbance trade-off. So what this information disturbance trade-off tells us is we want to consider the absolute best recovery map for any state in the code subspace. This is important. It says that the recovery map is general for a subspace. It's not that for every state in the subspace you choose a recovery map. And this is a difficult optimization problem, but the information disturbance trade-off tells you that in fact it's the same as considering basically this property 4 that we had before. So how close row ACR is to a tensor product state between A and CR. And here you only take the infimum over states. And for this exact equality to hold, you need the Beer's distance. The diamond distance is not going to give it to you. So we see that relationship 3 and 4 can be recovered exactly for approximate codes. Now, on the left-hand side here, we still have an optimization problem, which is very complicated, meaning we have to optimize over all states on region A. But of course, there's a very natural state to choose on region A, which is just a restricted state row on A. And so the second result that we get is that if we choose this much simpler to the original measure we chose. But now what we pick up is a different order of the error, right? So although they're equivalent up to a square, there's still this square root difference, not equivalent up to a constant. So we can recover relationship 2, but we have a different scaling with the error. And then finally, we'll also be able to show that a type of cleaning lemma holds. So this says that if for any logical unitary acting on ABC, there exists an other operator which is not going to be unitary that acts only on BC, such that its action on the code subspace is going to look almost like the unitary. And then the converse is essentially the same statement, but you lose a notion of locality. But of course, you can't really have a notion of locality if you just start from a statement about unitary operators, which are global. Fine, so we recover this fifth condition. And conspicuously, the one thing we were setting out to show was roughly the same, we're not able to connect. So we actually think that local topological quantum order, which is one of the fundamental definitions of topological order in condensed matter systems, is really slightly different from these notions of approximate error correction. And we really don't understand that quite yet. So let's see how it plays into the approximate Bravi-Poulin-Terral bound. So if you remember, in the first step of the proof, where we need to construct the largest correctable squares, the very important thing is we needed to use two definitions of approximate error correction. In this case, it was number 3 and number 4. But then you need to use these iteratively, which means that if they weren't exactly the same order and you applied them iteratively, then the error would change exponentially. So you'd completely lose the applicability of this lemma, which tells you that if you want to generalize the BPT bound, this definition 3 and 4 absolutely have to be the same. There can't be any separation between the two. Then the union bound, all you really need is locality of the recovery map. And that's why we define our recovery map to be local. And then for the rest of the theorem, everything essentially carries through unchanged. So basing ourselves on the original argument for the Bravi-Poulin-Terral bound, we're able to derive what we think are the relevant definitions for approximate error correction codes for topological systems. Of course, you pick up a lot of epsilons and deltas, but that is somehow, it is technical work, but all of the all the physical insight somehow is the same as in the exact case. Okay, so I think I'm going faster than I anticipated, but that's fine. The obvious question is, are there any examples for this, right? So the reason that almost no one in this room has worked on approximate error correcting codes is that there just haven't been any good examples of approximate error correction codes. So for practicality, it's not that relevant, or it seems not to be relevant. So one place where we actually can find an example which fits straight into to our framework is if you take a commuting projector code and you slightly perturb the projectors. And there what you get from a series of very important results in the theory of topological order, namely that topological order is stable, we immediately recover one of the properties of approximate error correction and can just extend this model to our framework. Somewhat, that's not very satisfying. It's sort of the models we already knew. Okay, good, they were stable. We sort of assumed they were stable. It's not very interesting. But the second example I want to cover are these Mera codes. So, and I'm going to argue that these are an interesting class of approximate error correcting codes. So I'm really going to change, I'm going to shift focus here. So everyone who was sort of asleep with the epsilons and deltas can wake up now, and we're going to cover something else. So a Mera code is constructed from a Mera tensor network. So for those of you who haven't seen Mera tensor networks before, the bottom layer here represents the physical space. And acting on the physical space, you have blue unitaries called disentangling unitaries that act on neighboring qubits at each level of the network. And on top of the unitaries, there are isometries, which shrink the dimension of your system. So in this case, with what's so-called a binary mirror, the dimension of the system is divided by 2 at each level of the mirror. And what you usually do is for a finite system, say on a ring, you'd perform this process all the way up so that you're just talking about a single state. But what you can is, of course, cut the construction at a certain level and then consider a subspace up here that gets mapped onto a subspace of the same dimension at the physical level. And this is simply going to be an encoding map. So, intuitively you think, okay, wow, this is already pretty close to an error correcting code. But of course, this is just an isometry between one subspace and another subspace. A priori, it doesn't have anything to do with an error correcting code, meaning that, well. So before I get to why we actually chose this example, study this example in the context of approximate error correction, there are certain other things about this construction that one should pay attention to that are really quite remarkable. Is that if you consider an observable at the physical level, that's represented by this green box, you'll notice that if the observable acts on 3 sites at one level, it's also going to act at 3 sites on the next level, and it's going to act on 3 sites at the next level, and so on and so forth. So it preserves locality from one level to another. Furthermore, if you have an observable which acts on many sites, it's going to act on fewer sites at the next level and fewer sites at the next level until it reaches this, what do we call it, unit cell of 3 sites, and then it's going to act locally on top. So you sort of have a 2-phase process if you look at the action of observables on the network, where first you have a shrinking of the support, and then you have a constant support. So that's the first property. And then the second property is since U is a unitary and this triangle is an isometry, if you take 2 copies of these states, you invert them together and you contract them, then as long as there's not an observable in between the contraction, then the unitaries cancel out. So this is a unitary and its conjugate, and the isometries cancel out. So what you get at the first level, if you just have a local unitary, is that you get a mapping from 3 sites onto 3 sites. So you're mapping a state from one dimensional space to the same dimensional space. And this can be interpreted as a channel. And what's remarkable in this construction is this is, in fact, a quantum channel. So a completely positive trace-preserving map in the Heisenberg representation. And these channels have also a lot of useful properties. They're sort of the workhorse in quantum information theory. But a generic channel is going to have a unique stationary state. And this unique stationary state is going to be full rank. What this in particular means is that if you apply the channel n times on a given observable, then you're going to get something which is close to the identity times the expectation value of the observable with respect to the fixed point of the channel up to an error which is exponentially good in n. Okay. So let's get back to approximate error correction. So now we're really going to use this machinery that we developed in the previous part, which is to say we're going to start with our intuitive or operational definition of error correction, map it onto this simpler formulation, and then map it again back onto this even simpler formulation where we just have to see how far the state on rho ACR is from rho A tensor rho CR. And then we map it down to an even more familiar distance measure, which is the trace norm. And we reduce the problem of showing that the Mera code is in fact an approximate error correcting code to just showing that any code state satisfies, well, where the trace norm is going to be small for any code state. And how does one do this? Right, so this is the basic result, is that for any state in the mirror code, if you erase a region at the physical level, then you can recover it up to a precision which depends upon the size of the region you erased divided by this local region where the recovery map acts to some power. So you realize that it's an approximate code, but which scales polynomially rather than exponentially well. And now, okay, we've been through a lot of proofs already, but the proof of, of this expression is in fact almost the same one that was used for decay of correlations in the original Mera papers, simply by observing that to bound this term, we use a variational characterization of the trace norm. So this is going to be the same as a supremum over all observables or emission operators of norm 1 acting on these states. And then one observes this natural behavior of Mera codes. So you can express the expectation value of the physical state with a physical observer as the expectation value of the state at a higher level times the mapping of the observable at the higher level. But note that the support of the observable has changed when you go to a higher level. So the support of the observable can be very non-local, but then gets mapped to something which is highly local. And if we start with an observable ACR where A has support just on 3 sites, then we can break it up as a Schmidt decomposition, and there are only going to be finite number of Schmidt coefficients here. And then when we go higher up into the circuit, we use this property of CPT maps that this expression is very close to the identity. And once it's close to the identity, this term is just the same as the right-hand side. So somehow the success of the approximation depends upon not how fast you converge to a unit cell, but once you're at a unit cell, how farther you still go. So we've constructed an approximate error correcting code, although it's, I mean, what we might hope for in an approximate error correcting code is that the error is exponentially small. Here the error is only polynomially small. But then we'd like to see what we actually can do with it. So the first thing we observe with this code is that we also can establish a trade-off bound. And K got capitalized for no reason. And what we find in our code is that the trade-off bound is given essentially by this uber holographic scaling. But unfortunately, we have a slightly different scaling than what Fernando and John came up with. And ours is a bit tighter. And I believe the reason for this is that we don't impose the entanglement wedge hypothesis in our codes. In fact, they often don't satisfy them. And therefore, we get a weaker bound. The second thing we can do with the same machinery is we can obtain a type of Lieb-Robinson bound, meaning if we consider an observable deep in the bulk, I forgot to say that if we want to connect to notions of holography, the way the system would be interpreted now is that the physical system is the boundary, and this virtual, what's considered a virtual system in the Mera setting is now interpreted also as a physical system, but in the bulk. And now you can talk about local observables in the bulk compared to local observables in the boundary, and one can derive Lieb-Robinson bounds, so the speed of information propagation between bulk observables and boundary observables. And this is relevant because it, in a sense, gives rise to dynamics in the bulk, just from entanglement properties at the boundary. This is one of the core goals of this desire to study the holographic correspondence using quantum information. Now, in the setting of holography, I think this is a very relevant example because, as far as I know, most of the examples previously that tried to study holography using error-correcting codes just postulate an error-correcting code and show that it has a lot of the same properties as that you'd expect from the ADS-CFT correspondence. Whereas here we just start from an entanglement structure, and we show that this entanglement structure is just an error-correcting code. So it's a much more constructive approach to it. Although unfortunately, our system doesn't satisfy a few of the properties that people would like. We consider a useful toy example, and especially it gives us some access to dynamics. Okay, so that's all the results I want to talk about. I'd like to mention a few open problems. And I'd say that the overwhelming open problem is finding more and more useful approximate error-correcting codes, because the examples are still pretty, well, they're few and far between so far. I think a very interesting technical problem is, if we take these mirror codes seriously, well, how do you actually decode information in them? This is completely opened. One of the things I'm more interested in is, okay, there are several definitions of topological order in condensed matter systems, many-body systems. But one of the core ones, this local topological order definition, depends crucially on the fact that you're dealing with a frustration-free system. And as soon as you move away from frustration-free systems, it's very difficult to define things properly. And perhaps some of the insight from approximate error-correcting codes, which don't fundamentally depend on frustration, can lead us to understanding topological order in these non-frustrated systems a bit better. And finally, I think it's important to investigate dynamics or fault tolerant a bit better. And something we've been trying to do, but sort of conspicuously failing at for a little while, is trying to extend the Easton and Knill theorem to approximate codes. So that I want to finish my talk.